Hello everybody, hope we're all doing okay. We are not in chapter 5. What the heck chapter? Are we in chapter 5? No, we're in chapter 4. I was like, wait a minute, that is so wrong. So, sorry about that. 4.5. 4.5. Okay, so 4.5 is derivatives of logs. All right, so you knew it was coming because I asked you to review your log properties, so you knew this was coming. But actually remember that in this class, we're not focusing on all logs. We are only focusing, remember, on e to the x, which means that what we only really need to look at is the ln of x, okay, which makes our life super easy because the derivative is not that bad. Okay, so remember, so we're looking at f of x equals the ln of the absolute value of x. Now, we're in a situation here where a lot of the times this absolute value doesn't apply to us because we're doing business problems anyway, and so we're looking at positives, okay? But this is important that we remember that when you put a negative or a 0 into that log, you're gonna get an error. So it's important that we remember that the absolute value, that always has to be positive, okay? Always has to be positive. All right, so if we want the derivative, so d dx of the ln of the absolute value of x, okay? Like I said, this is not that bad. This is 1 over x, okay? So the derivative of ln of absolute value of x is 1 over x. So it's not as nice as e to the x being its own derivative, but it's not that bad either, okay? It could be a heck of a lot worse. All right, so it's definitely on the simpler side. But what that means is just like with e to the x, what we're gonna see here is a lot of using the product rule, the quotient rule, and the chain rule. So when they ask us to use this, there's gonna be a lot of extra crap thrown in there. Okay, so let's look at some examples just to start us off with, and then you'll see what I mean. So let's say that g of x was x times the ln of x, and we want to find the derivative. So not just ln of x, but we've got the product rule going on there. Okay, so like I said, this is definitely the way you're going to see this. So if we want g prime of x, we got the product rule, so we'll say the derivative of the first is just 1, and then we'll leave the second. So we're left with the ln of x, then we're going to go plus, then we leave the first, x, times the derivative of the second, which is 1 over x. So if you notice, some nice things kind of happen, don't they? All right, so those x's there are going to cancel each other out, so we end up with the ln of x plus 1. All right, so let's see if some nice things happen if we try to use the quotient rule. So let's say that f of x is the ln of x over x, and you're going to start to notice that they come to a point where they start off with every single one has the absolute value and they're trying to remind you always positive, and then eventually they just kind of leave it off because you are supposed to remember that this should always be positive, okay? So that absolute value is always hidden back in there, okay? All right, so we got the quotient rule. It's been a while since we've used the quotient rule here. So f prime of x, so we've got low d high, right? So low would be write down x, take the derivative of the high, 1 over x, minus high d low, minus ln of x times the derivative of the bottom, which is just 1, all over the bottom squared. All right, so again, nice things happen there. So we're left with 1 minus the ln of x all over x squared. So, I mean, it's not the prettiest thing in the world, but it's not much more difficult than the original problem. And that's the nice thing about the ln when you put it in with the product rule or the quotient rule is it tends to do some canceling and makes things work out nicely. Okay? So definitely going to see quotient rule, product rule, but what we really want to focus on is the chain rule. So let's say the chain rule for ln x. Okay, so if we want d dx of the ln of f of x, so if what's in our log, our natural log, is not just x, but it's some function itself, then we definitely have to use the chain rule. Derivative of the outside, derivative of the inside. So what ends up happening is we're going to take that, whatever was in here, and it's going to go on the bottom of a fraction, right? 1 over x. Take whatever is here, put it down here. But what we need to do is include the derivative of that inside, and it ends up on the top of the fraction. Okay? So if you want the derivative, and you have to use the chain rule, put the original on the bottom, put the derivative on the top, and that's it. Okay? So it's not that bad. Again, it's not horrible. So let's see what we got here. So they say that h of x is equal to the ln of x squared plus 1. So if we want h prime of x, we know it's going to be a fraction because of the ln. We take the original guy in the parentheses and we put him on the bottom. X squared plus 1 goes on the bottom. Then we take the derivative and stick it on the top. So the derivative of x squared plus 1 is 2x. And then we would take a minute to see if there was any simplifying, you know, if we could. We can't in this case, but in case there was, okay, because sometimes these will simplify. All right. Now, you might think we're not ready for this next one, but I'm going to show you it's really not that bad. So let's say that the next one I had for you was f of x equals the ln of x cubed plus x times x cubed plus 2 to the 6th. Okay. All right. So this whole thing is in the natural log. So yes, at first glance you go, oh crap, I don't want to do anything with that because here it looks like the product rule, we've got that 6 up there, which means we're going to have the chain rule inside. This is a total disaster. And if it didn't have this, okay, if it didn't have that, I would agree with you. Product rule, chain rule, we're going to be here and step after step after step. But guess what? Because this is the natural log, this problem becomes actually very simple. But you have to remember, okay? So I asked you to review because logs have nice properties. So do you remember how if there's a multiplication in the log that you can split that into 2 logs using addition? So instead of jumping right into the derivative here, let's go ahead and rewrite. So we're still talking about f of x, no derivative yet. So could we rewrite this as the ln of x cubed plus x plus the ln of x cubed plus 2 to the 6th? Don't we have a property that says we can do that? Okay, now all of a sudden this one looks a lot simpler, looks a lot more like the last example, and then we've got this one over here. Now, this one still has a 6 up there, which at first glance, oh crap, there's still a 6, there's still this chain rule to use, but we've got another property. So what if we continued on, don't take the derivative yet, leave this guy, he's good, but remember that we have the power rule that says that we can bring any exponent and stick it out front. So we can say 6 ln x cubed plus 2. Okay. Which means that this is just a constant that just is going to come along with the fraction or with the derivative as we go. Okay. But what happens is we've taken this ugly thing up top, taken a couple steps, and now, thinking about what we did last time, this one's going to give us a fraction, and that one's going to give us a fraction, and we're going to be done. So now we're ready for the derivative. So first one, we write the fraction line. The original goes below, so x cubed plus x. The derivative of this goes above, so 3x squared plus 1. Now on this one, now remember, there's that 6 there, so there's going to be a 6 up top. That guy just comes along. Now again, though, on bottom, x cubed plus 2. And on top, we'll have the derivative of this, which is just 3x squared. Really not that bad, is it? Okay. Now, no matter what, I don't care how much you do here, but definitely don't leave that like that. Okay, so 3x squared plus 1 over x cubed plus x, and then make sure you turn that into an 18. Okay. So make things as simple as possible. Alrighty, look good there? Slide, give me a second. Okay, so let's look at another one that uses some different properties, but still the same idea. Okay, so this one says if we're given f of t, okay, we're going to see t a lot because in our word problems, T a lot of the time stands for time. So if we're looking at, interest, and we're looking at how much time is spent. So you got to get used to that C and the T there. So if f of t equals ln of t squared e to the negative t squared. All right, so we have multiplication here. Then we have an exponent, and that exponent is going to require some work of its own as well. So definitely not looking the prettiest thing, but remember, we go, wait a minute, I'm not going to take the derivative, I'm going to rewrite this first. So we're going to go f of t equals ln t squared plus ln e to the negative t squared. All right, now, it's a lot simpler, but there's still more that we can do, okay? If you wanted to take the derivative at this point, you could, but I'm telling you there's still more to do. So if we want, we can bring this 2 out front, but we can also do something here. Remember that the base on the natural log is like a little e, and we have a property that says if the base here, if the log and what's in the log match, those guys will cancel out and just leave us what was left in the exponent. So what we actually get here is 2 ln t, and then we're left with minus t squared. Okay, so that e on the ln, they cancel each other out. All right, now we are as simple as we're going to get, so we can take the derivative. So the first one has the log, and the second one doesn't even have a log, but so the first one, we got our fraction. Now there's going to be a 2 up top, right, because of this 2. Okay. We put the t on the bottom, and the derivative of t up top, which is just 1. Okay. And then over here we go minus, what's the derivative of this guy? 2t. Now, let's say that you didn't notice or you forgot some of these properties or you didn't want to do this pulling the 2 out front. So let's go back to f of t equals ln t squared plus ln e to the negative t squared. Okay, so just to show you that every step you take will make life easier, but you don't need to take every step. So if we want the derivative straight from here, fraction, t squared is going to go on the bottom, but now what goes on the top? Derivative is 2t. Then over here, fraction. Oh, that hideous thing is going on the bottom. But we need to put its derivative on the top. Now remember, the e itself is its own derivative. So its derivative is going to be e to the negative t squared multiplied by the exponent negative 2t. Okay, so the original here, and then the derivative, you write down the same thing, derivative of the exponent. But do you see how in this one, there's definitely some canceling that can be done. So a t can cancel here with 1 there, so we are left with 2 over t. And then boop, boop, those guys go away, and they leave us the minus 2t. So in either way that you do it, you get the same answer, okay, which is definitely something we need to make sure we get. You get the same answer. It just depends on where you want to do your work. Okay, do you like the log properties better? Do you not mind working with the fractions and the canceling? It's totally up to you. All right, so that idea though, never, ever, 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 ever do a problem that's in this form or this form. Simplify this thing first. Simplify, use your log properties. That's why we learned them. Okay, this is the only reason why we learned them, is to make logs easier. And that's what happens here, okay? It definitely makes logs easier. All right, now, we've got one other thing in this section, and this is something that you may never use, but it's just an interesting little tidbit that you can use if you want. And it's called logarithmic differentiation. Okay, give me 1 second. Make sure things are, yeah, things are still going. Okay, logarithmic differentiation. So remember that, back when we started, so like back in chapter 2, when we started dealing with the product rule and the quotient rule, some of us were not super duper fond of it. We're like, oh, great. And the mistakes were made or things got big and ugly and everything. Well, logarithmic differentiation is actually kind of like a shortcut, like cheater's way to find derivatives. You're still finding the derivative, you're just not doing it using the classical rules. So if you are comfortable with your logs, then all of a sudden you can be like, oh, I can do this the easy way. So let me give you an example here. Let's say that we were looking at the equation or the function y equals x squared times x minus 1 times x squared plus 4 to the 3rd power. So let's say that this is the guy that I wanted you to take the derivative of. Okay. Now, if we were doing this back in chapter 2, I told you I would have told you to do some simplification, like maybe distribute that in this. We're not going to multiply out, but when you look at this, are you seeing the product rule and the chain rule going on there? Okay, so the hope is that you're seeing that there are multiple steps to this problem. But we can, if you don't want to deal with all those multiple steps, we can do something a little bit tricky. We can take the natural log of both sides. So we are going to take the ln of both sides. So we're going to write this as ln y equals ln x squared, x minus 1, x squared plus 4 cubed. Now, our reason for doing that is because those 3 things that were in this original function, can we now use log properties and split them up into 3 simple pieces and not have to deal with the product rule at all. Okay. You see where I'm going with this? Now, the only problem is this out here. So we need to have some way to deal with this. So this is where we're going to use implicit differentiation. I gotta find my purple pen is starting to run out, so let me find another pen here. Let's go with the red. Okay, so let's use implicit differentiation. Okay, so implicit differentiation, that's where you take the derivative of both sides, right? Okay, but before we do that, we're going to do some simplifying here. Remember, don't be doing it right now, but we're going to use implicit differentiation. So first, let's split these guys up. So we're left, we still have the ln y on the one side. Now we're going to have ln of x squared plus the ln of x minus 1 plus, and can we bring that 3 down? 3 times the ln of x squared plus 4. All right, now comes the implicit differentiation. So it means we have to take the derivative of this side. So remember, for the derivative here, we take the original and we put it on the bottom, y. But remember, in implicit differentiation, whenever you're taking the derivative of a y, you need to follow it by y prime. Okay, so this side is going to end up being y prime over y. Now on this side, we're going to put the x squared down below, and then the derivative of x squared is 2x, goes up above, plus, what goes on the bottom here? X minus 1. What's the derivative of x minus 1? 1. Fraction here. Now remember, you're going to have 3, yes? So 3, put x squared plus 4 on the bottom. And then derivative would be 2x up top. All right. And then one more thing you have to do, because we want y prime alone, so we say y prime equals, and we're going to multiply both sides by the y. So you put y times, and then let's do a little simplifying there. 2 over x plus 1 over x minus 1 plus 6x over x squared plus 2. Now, that derivative does not look like the derivative if we had done this by, using the product rule and the chain rule and everything. This would have looked a lot different, okay? It definitely would, there wouldn't have been a fraction, right? Because there aren't any fractions in the original. But that doesn't mean that this is wrong, okay? It just means that it's in a different form. So, wrong, right, okay? So, but we got it. We got the derivative. We just did it a different way. Okay, so one more of these and then we'll call it quits. All right, so let's say that I wanted you to find the derivative of y equals the square root of 3x to the 4th plus 1. Oh, wait a minute, yeah, sorry, I know what I'm doing. Over x squared plus x. Okay. Look all right? Okay, so back in chapter 2, this is definitely a problem you could have seen. It would have been one of the more difficult ones, but you definitely could have seen that. Now, division means we're looking at the quotient rule, okay? Square root means we're looking at the chain rule, so we got some stuff going on there. Yeah, what if you don't want to do that? What if you've had it with the quotient rule? You're like, I don't ever want to do that again. Well, we can use this logarithmic differentiation again. So we're going to log both sides. So we're going to say the ln of y equals the ln, and then we're going to put this whole thing in there. Now I'm going to make the change right now to write that as 3x to the 4th plus 1 to the 1/2 power over x squared plus x. Now, remember, We didn't include this natural log. We didn't do this to make this harder. We did this to make this easier, because when you see a quotient in a natural log, you can rewrite this using subtraction. So this we can rewrite, so no derivative yet, rewrite ln of y equals ln of 3x to the 4th plus 1 to the 1/2. Well, actually, can we put the 1/2, bring the 1/2 and put it out here? Right, so 1/2 ln 3x to the 4th plus 1 minus the ln of the bottom, x squared plus x. No quotient rule, gone. No chain rule, gone. Now, if we want the derivative, remember we got to take the derivative of both sides. So the derivative of the one side, we put the y on the bottom, y prime up top. Okay? Now, first fraction here is going to have a 1/2, which means there's going to be a 2 on the bottom. Then this guy also goes on the bottom, 3x to the 4th plus 1. Okay? Up top, we're going to put 12x cubed, right? That's the derivative. Then don't forget your minus. On the bottom of this guy, we're going to put x squared plus x. And on the top, we're going to put, derivative is 2x plus 1. Okay. No quotient rule. Still have fractions, but no quotient rule. Now remember, we need to take the y and multiply it to both sides so that it's just a y prime left over here. So we have y prime equals y times, and then I'm going to do a little reduce here. Boop, boop, boop. So 6x cubed over 3x to the 4th plus 1 minus 2x plus 1 over x squared plus x. So I always thought of this as, it's not cheating, there's nothing wrong with it, but I always just thought of this as a shortcut way to get what you want. And I must say there were a couple times I used this on a test because I didn't want to find the derivative of something. So imagine if you have the product rule and the chain rule and the quotient rule all in one problem. If you can split that apart, life gets super easy. So it is kind of a little bit of a cheat, but hey, if you like it, it works. Okay? Alrighty. So logarithmic differentiation is not that bad, is it? Okay, not that bad. Don't worry about it. But remember, this is for the ln, regular logs, log base 2, log base 6. No, okay? ln works nice for us because that's the only one we're interested in. Okay? Phew. Another one done. All right, see you next time.